So last time we stopped at this curve, and this curve I said this is a scale, and that is a ratio between the amplitude of the steady state response to the static diffractions. And this is the ratio of the working frequency to the natural frequencies. And here we are given us another term, and we define this ratio, the amplitude of the steady state response. Okay, and here you need to be very clear about what amount, what quantity you are working on, because right now you can see more and more, I would say, definitions of the terms or terminology will be taken gradually. So you need to know what kind of things you're working on. For example, you calculate the total response, or you calculate transient response, or you calculate the steady state response. The different terms have the different meaning, even the different quantities. And this one is the magnitude, ratio of the magnitude of the steady state response to the static diffractions. That ratio we give a name called the magnification factors. Magnification, that means due to vibrations, the amplitude of the steady response will be amplified or de-amplified, but by all means we define that as the magnification, that is the system response due to vibrations. Okay, so that is this term defined by this. So that's another term. So that is what we have from last time. And so from this page, basically here we start with our total, the expression for the total response. Again, this is the equation we have known so far. This equation is meaning this is the total response, okay? And if you kind of taking the notes or have a slide with you, try to annotate this is a total response. Total response, that is response including transient and steady state. So that's a complete description of the system's dynamics. This one including the influence from initial conditions, which means associated with these terms and this term. Okay. If you like, we can reorganize this term into this, and how we do it, basically in this expression, equation 2 is identical to equation 1, and by doing this, we simply associate the term with initial positions. We stand out that term. We associate with the initial position and the velocity, we get that term stand out, okay? Then combining the remaining term, that means the coefficients, the terms with this term as the coefficient, we're combining the two terms together into this. Okay, so that's a reorganization, and that's a way for other purposes not leading to our discussion today. So basically the two terms are identical, okay, and we rearrange. So basically the first two terms are our transient response, the last term regarding our steady state response, okay. In this way, if you want to further simplify, you can replace this term, that is the magnitude of the applied force divided by k. So basically this term is what we define the static diffraction, and using the symbol delta st. Okay, if you like, you can replace this term as a delta st. And so once we say open book or open notes, and then a lot of the information in the textbook, hopefully you can get yourself familiar with all the kind of the symbols, something like this one, okay? And so today's focus, we're going to simplify the equation 2, okay, based upon certain scenarios. So depends on our choice of the working frequency omega, okay, and we're going to have the further detailed discussions. For example, when omega is chosen to be natural frequencies, undamped natural frequencies, that means this scenario we call the system is on the vibration, on the harmonic excitations at the resonance frequencies, okay. So basically we try to apply the force, apply the loading, such that we drive the system crazy because we oscillate, we vibrate at the resonant frequencies. That means under this situation we can use the minimum amount of the power or energy we can drive the system, basically load it up. Okay, basically drive the system to a singular state, unstable state. And then the remaining two are either the frequencies is larger or slower, and the two are very generic, not much to say, but we're going to focus on this one. And maybe a fourth course, the fourth case would be if the working frequency is not exactly equal to the natural frequency, but the working frequency is very close. If they are very close, and then what happens? So that is the things we're going to go over today. The first one, yeah, my note, I don't have anything. Okay, so the first one is when we chose the frequencies, working frequencies to be equal to the natural frequencies here. So basically we say the system is under resonance oscillations or under resonant vibrations. So again, we start from our the most complete description of the equation. Again, this equation is copied from here, okay? This one basically equal to this one. So again, this one is our complete description. This equation including transient solution and steady state solutions. Okay, I want everyone to be very clear what we are doing. So this is the total response. Okay, so now for this case, if when omega equal to omega n, so under this case we want to simplify the terms for this specific scenario. And again, if you pay attention to look at the slides here, and I just want to show you the spatial condition that's going to happen. So you can see when omega equal to omega n, the denominator is equal to 0. And when omega equal to omega n, numerator equal to 0, basically the last term that associated with the steady state basically is 0 divided by 0. So for this case, we can apply the calculus. I forgot the name, the name of the term, but basically in that technique is this. If we have any functions and approaching to the particular value when that numerator denominator both going to 0, then we simply take the derivative on each of them. Then we proceed to evaluate that kind of singularity situations. So that is the technique we're going to apply for. Okay, so that means when we do the limit and find the limit of these functions, and both are in the limit, both will be zeros. So we simply take the derivative on the numerators and take the derivative on the denominators. So we come to this one, then we calculate the limit. Hopefully you remember that kind of technique, right? At least 2 or 3 guys kind of knock your head. Thank you so much. Okay. So under this case, then we calculate the limit is equal to this one. Okay, good. And equal to this one. So simply we replace this term. We replace this term by this one. So that equation 2, again, under the resonance situations, that becomes this one. Okay, again, the first 2 terms unchanged. That is regarding transient response. And then the steady state response become like this. And we do a little bit more scrutinize in this term. This term is cosine with constant, so basically that is the cosine, and this is the sine with certain constant, so basically the sine curve. The both 2 terms basically give us a constant harmonic output. Okay. However, for the last term, that one you can see that is the sine functions. However, the coefficient is this one. Coefficient is a constant divided by 2, multiply with omega n, that is constant, multiply with t. So when t goes by, go to infinity, this term will drive. That means if you look at this one, if you would imagine this is the amplitude of the sine curve, then that amplitude is a time function, is time increasing. So in concept, this is a profile defined by this linear function of t, right? So that means eventually the vibration is going to just like this. And when time goes by, that getting larger and larger, we call this system as to be unstable, right? Okay, so unstable, that means the physical application is the displacement. This is the steady state response of the degree of freedom. And that means the system eventually, what is a steady state response? Steady state, that means perpetual response. So eventually the system degree of freedom, or X, going to be very large. How large? Until the system's material wouldn't be able to afford such deformations. So that kind of regarding linking to your mechanics material or other kind of machine design. If you have a deformation, and deformation getting larger and larger until the material cannot hold it, simply break it up or fracture it. Okay, so in reality, the fractures will happen in some way when the material really failed. Okay, so but in theory, in kind of mathematics, we can express by this. So that is a situation. This term will drive the system to fail later. Okay. So that is this case, and if you like, I think this equation also appeared in our textbook. And if you like, you can highlight this term. Okay, in particular, you can highlight this term here, and to help yourself. And once later on, once you do the homework and you kind of turn over the notes or something to refer to any useful information. And now will be the moment, if you have any marker, you can highlight this term. Okay, just remind yourself. Okay, so that is for the first case. Yes?
So I looked up the limit rule. It's called the Habermas rule.
Thank you so much. Thanks. Okay, and then the second term is, the second case is when the working frequency is less than this, but this is very general and I would say not much to say, but we can go over the things. Again, this is the very generic equation 1. Again, that is the equation we obtained last time. Okay, so again, for this case, so this is a very generic equation, and again, remind everyone this equation is from the one we got last time, and that is one we can go back to the few slides here. So again, this is the total response, and that equation is copied to here, okay? So for this one, we can do a little bit another organizations to help us. So maybe we can try is, again, the first, we combine the two terms because the two terms are the in harmonic oscillations in terms of frequency omega n. So we can combine the two terms into this. And basically, using our exercise in homework 1, we will be able to calculate the magnitude, and that is basically the square sum, the square root of the square sum of the two terms here, okay? And this is the phase angle. Basically, again, you can calculate it from there. So by all means, we have the equivalent expression like this, and we leave the terms here. This is the steady state response. And again, to here, we can further the simplify. Basically, is the way is we simply divide the numerator denominator by k. So if you like, maybe this one, we can say this term is simply equal to delta st and 1 minus r squared. Okay, that would be the simpler kind of the symbolic expression. Either way, it's not that important. Okay. So basically, for this one, the result for this case simply is the linear combinations of two harmonic functions. One is in cosine oscillation of the frequency omega n. The other one is in the frequency of omega. We simply do the combination of the two cosine functions of the different frequencies. So doing this one, and if we are given numbers and do this kind of superposition should be easy, either do the program in MATLAB or even Excel. And we can combine adding the two curves together, okay, numerically. But here we want to show the symbolic, and the way is this. Okay, right now for this case, we're choosing frequency. Working frequency is small, so maybe let me note this is a smaller, and this is the larger. Okay, I just make my note. Okay, so that means this term oscillate slower. This term oscillate quicker. So symbolically, we try to do is this term here. Oscillating slower, we exaggerate the difference. So basically this term regarding is a slower oscillation. That means it's regarding this term here. Okay, with symbolically, basically omega, that is the working frequencies. So from peak to peak, so from here to here, that is the period. Period equal to 2 pi divided by the frequency. Okay. And then superposed to this curve is coming from this term here. Oh, by the way, for this case, we can define, for this term, we can define its amplitude. The amplitude of this is given by this, okay? So that is the term by there. Okay, now superposed to the blue curve is the curve from this term. So this term oscillate more frequent, and that has the omega n. So that means the oscillation with magnitude. So this is the magnitude, and with the sinusoidal curve, and at the higher frequencies. So basically that is oscillating like this one. Okay, and then the frequency of this. So maybe in this way from peak to peak, and that frequency is 2 pi divided by omega n. That's it. So this is symbolic, kind of the schematic showing of the superpositions. Okay. Again, this one is not to show off our mathematics. No, this one simply just want to tell you kind of how the curve and the response look like. And the best way to learn this topic is we directly work on the numbers. If we are given the numbers, I simply ask you to draw this response. Then what you're going to respond to my question is you simply go to MATLAB or go to Excel, and whatever the tools make yourself and can make this curve happen. Okay, so that is this case. So vice versa, if we have the chosen, if we have the different case, for example, another case is omega is larger than omega n. The same situations, again, I can tell you the equation, we do the similar simplification. Equation 4 is identical to the previous equation here. The two equations are identical. So the same thing, you simply draw the response superposition of the two curves, and then just something like this. Okay, but again, when you draw the curve, then this one, omega n, this term right now for this scenario, this one oscillates slower and this one oscillates quicker. So basically that one you redefine your kind of drawing. And the two cases is not much to say. And the best way again to work on the numbers will be good. Okay. Questions? Now the last case, if we chose the working frequency, if that working frequency, we try to avoid the resonance, but we want to approach. And so that case is, for this case, is the working frequency is very close to omega n. They can be a little bit larger or can be a little bit smaller, depends on whatever, okay? So this one, I can tell you, before we go to the detail, the response of the system, again, this is a total response from our general situation. And for study this case, we can do a little bit, we can help ourselves a little bit easier. We try to not to including any influence from the initial conditions. So again, for demonstration purpose only, we can ignore the influence from the initial conditions. And that means we can set up the Q equal to 0. And I think right now I said we can ignore the influence from the transition conditions, from the initial conditions. And that means for damped systems, the initial conditions, the influence from the initial conditions will be damped out. Okay, so that means for system with damping, which basically exists in almost all the systems in the world, and they always have a damping. As long as they have a damping, then the initial conditions influence will be damped out. Eventually, the transient response will go to 0. So in this case, I would say we feel good doing such a simplification. Basically, we are okay. So under these situations, then the response will be like this. That means for these illustrations, we don't consider the transient response. So that means for the total response, by eliminating the transient response, then the total response simply is equal to the steady state response. Okay. So that under that situations, the response will be like this. So the systems, the oscillation will be something like this curve. Okay. So the curve just something like periodically, the two system will be oscillating like this. But in kind of the pattern, periodically they have the kind of the amplitude kind of the something like this one. Okay. So these questions for these formulations like this, that is particularly related to the homework question 1. Okay. So for the homework question 1, and after introducing the hint I provided in the problem statement, then eventually you will get is something like this form. Okay. So something like this form, maybe using this as the example now would be a good time for me to, we can investigate what that means, the amplitude of vibrations. Okay. So the amplitude of a vibration is like this. We know if we have the regular sine or cosine functions, okay, so that is a regular cosine or sine function. For such a case, and for example, that is a cosine and say a theta t. Okay, so for this case, we simply know by definitions that is the amplitude. A is called the amplitude. Amplitude, that means the magnitude between 0 and the peak. Okay, that's the definition called the amplitude. That is the very basic, very generic definition for amplitude of the oscillations. How about for this case? From here you can see if we follow the definition of the amplitude by defining the difference between the 0 and the peak. So from here you can see the amplitude is changing over time. Right? So for the problem statement, for the problem homework 1, for the homework 3, this homework, the problem 1, I revised my statement by adding one word, maximum amplitude. Okay, so if we, for that particular homework problems, I say if the maximum amplitude equal to 0.02, so for that case, if we have such one, then basically you're looking for is this value equal to 0.02. Based upon that information, you go ahead to solve for certain numbers there. Okay. If I wouldn't revise this problem statement, then that was some sort of ambiguity. And actually, one guy showed me his kind of the work in progress, and that kind of triggered me my thinking. Basically, he tried to looking at the every possible situation. He look at this amplitude, look at this amplitude, this amplitude, this amplitude. You look at all the possible amplitudes, and then from there try to proceed. But he kind of stuck there. So I think that's a good thinking, but make life easier. Then we simply I just added the maximum amplitude. Then we start from there. Okay. Okay. And this phenomenon, we're back to our topic. This phenomenon is called beat or beating. Okay, and here for this is the final form, and in particular in this final form, everything are the same except we have a new parameter epsilon. Epsilon simply by definition is the twice of the difference of the frequencies here. We simply define the epsilon by this term, okay? And don't ask me why introduce 2 here, but simply just make the, I follow the textbook. If you don't like to, then you can come up with your own versions, but we follow our textbook. So simply we introduce the epsilon in this form, by this form here, then the total response, which means the steady response can be like this. Okay, so for this case again, this is we can draw the response that this time is a multiplication of the 2 sine curve, and we can draw that one. So the curve will be like this, and then here we this one again. This is defined as for the beating. Okay, and the beating. The definition of the beating, we call this is 1 beat. 1 beat, that means the period between 0 to here, we call it 1 beat. Okay, and another beat. Okay, so that one, the period of the beating basically is defined by this period. Okay, this period is how much, and that one simply equal to the half of this whole amount. That the whole amount, that one basically is this term here. Okay. So here we said this the and then this is the frequency of the beating simply is the difference of this. By just doing such the mathematical description, I don't think I will give you enough impressions. I knew the speakers of the computer doesn't work. Let me try. Okay, so here we have a certain application of the using the beating phenomena. Before I try using this, if everyone have played piano, and if you or you know about the pianos, and you know sometimes when you were young, your parents called some professional guy come over here to tune the pianos, right? No, you don't know what I'm saying. You know the piano in the back, they have so many strings, and if you, I'm not, okay, if you play the piano well, then your ear should be trained very well, and you sometimes you tell, hey mom, not always, but most of the time we approach to mom first. That tone is off a little bit, right? So we call the people to come to tune. And that kind of spend about 1 hour and tune all the way through 76, I think, beat the keys. Couple $100, okay. So how they tune? They must have some kind of absolute reference help them to back the tone on the right tone, right? So what they did is they're using the beating, okay. So what they do is this, for example, for this string, say C, and no C here, and say suppose that corresponding frequency, I forgot, but let me make up one. So that's supposed to be, say, 500 hertz, okay? And right now the piano at home is off a little bit, say 490 hertz. So basically here, to me, is the same. But for some guys, they really can hear this. So the person he come over here is simply to, he have a certain device, and something like this, and he just knock it, and that device will be, say for example, that device can produce exactly 500. Okay, the target is 500, and your piano for that particular string, that key is 490. So the two frequencies are very close. So when he knock it, this one, and when he press the piano keys, then the beating phenomena will appear. Then that person, even for regular people like me, I can hear, oh, the sound is wow, wow, wow. Okay, that is kind of beating phenomena. Let me try if this speaker is available. Otherwise, you can just go to YouTube. I got this one on YouTube, okay, and play with. No, doesn't work. The speakers. I know the speakers is, they must have a speaker. So this one is 250, okay, and this one right now he's trying is 238. So from the YouTube, if you have time, then you should be able to hear kind of the interesting kind of the whoa, whoa, something like this one. Okay, so as long as that person have this kind of the hearing, then he can gradually tighten up or loosen the string in from back of the piano until he cannot hear this kind of beating anymore. Then he pretty much get that particular key tuned. Okay. So that's the situation. So that we